Suppose that you're designing a fixed tilt solar PV system for a client, and the space that this fixed tilt solar PV system is going to occupy is either going to be purchased or has an existing opportunity cost, meaning that the client can generate revenue from another source of income other than solar. How does that purchase or opportunity cost play a part in the system's optimal design? My name is Mustafa Yusuf and I'm an engineering consultant at Neighbor Power. In this video, we're going to look at how we can marry space and equipment costs such that we can arrive at an optimal solution that minimizes the total system cost. Data by the EIA in the US suggests that most utility scale systems in the US are installed with a tilt angle that is substantially lower than their latitude value. This means that there is actually a compromise between space and equipment costs, especially as module and balance of system costs continue to fall. However, I have not seen this relationship articulated in the literature, and my guess is solar engineers and designers are still relying on ad hoc numerical methods to determine this optimal solution. In other words, they are running through all tilt angles and they are determining the system design, and they're picking the system design that has the lowest total cost, which includes both equipment cost and space costs. In this video, we're going to create a very neat and simple geometrical model which can be applied to both monofacial and bifacial modules. And we're going to show that the optimal tilt angle is actually a very neat and quite revealing solution. And it's actually so simple that it can allow you to communicate your design's space requirements at the preliminary stage of the design. So let's get started. So I wrote a paper about this, which you can follow along, which I will go through during this video. So before we get started, let's just be clear on what we are trying to achieve. So we know what our installed or equipment cost is in units per watt. We are also given a unit cost, a cost per unit area, and we are given a certain amount of energy E to produce. So given these three variables, we want to determine the optimal tilt that will minimize the total system cost, including both equipment and space costs. If space costs are negligible, the optimal tilt angle will be very close to the latitude value because that's going to minimize your equipment costs. On the other hand, if land is $50 a meter squared, you can just forget about the equipment costs and you're going to do whatever you can to minimize the space costs. So this is the point of this paper, is we're given essentially these. So we're given a cost per watt, a cost per unit area, and a certain amount of energy E, and we're trying to determine what is the tilt angle that we should use when building the system. Okay, so let's get started. I'm not going to talk about the literature review. So let's just get to the section 2, section 2.1. Yield is only a function of tilt. So of course yield is a function of several variables, weather, local anomalies, and so on and so forth. For our purposes, yield is simply a function of tilt, and of course a solar array is either facing south if you're in the northern hemisphere or north if you're in the southern hemisphere, and you can't be that close to the equator because there is really no optimal tilt angle, or the optimal tilt angle is just 90 degrees. So this sort of exercise is kind of useless. Okay, so we're not going to worry about degradation or anything like that, and the relationship between energy production and the system's capacity or the system size is simply P times Y. So if your system has a capacity of 1 kilowatt and an expected yield of 1100 hours, it will generate 1 kilowatt times 1100 hours, so 1100 kilowatt hours. It's a 2 gigawatt system with a yield of 900, it will produce 1800 gigawatt hours per year, so on and so forth. So for this paper, to derive that relationship between tilt and yield, I used data from NATE's solar array in Edmonton, Alberta, Canada. So at NATE, we have a multi-tilt solar array, 14, 27, 45, and 53 degrees, I believe. And using that data, I did a first order regression and some statistical analysis, and the results are in the paper as well. We're going to run through them. Whatever we do, we have to make sure that our system produces a certain amount of energy E. The higher the P is, the lower the Y can be, and vice versa. So, and as I mentioned, an array with an optimally producing tilt is a tilt that is equal to or slightly less than the latitude value. So for example, at NATE, the 45-degree module produces just as much energy as the module with 53 degrees, which is the latitude value for Edmonton. And that is because silicon solar modules are just better at capturing high light intensity than they are in low light intensity. So the module captures more incremental summer production than winter production. So the point of this paper is not to determine what that optimally producing tilt angle is. As you'll see in the statistical analysis, the coefficient of variation is about 6%, so there's no point in doing a polynomial fit or trying to determine that accurate angle. There are so many variances in your way that will impede you from getting that accurate fit. So no point in splitting degrees here. The only thing that this model depends on is that there is a global maxima when it comes to tilt. In other words, the optimally producing tilt is above zero and there's only 1 point. And we're not concerned for tilt angles greater than the maximally producing tilt angle because they will produce less amount of energy and use more space than lower tilt angles, so we can rest assured that our feasible space or the feasible space for the tilt angle that we're looking for is somewhere between 0 and that maximally producing tilt angle. So what is a solar array? A solar array is made up of many solar tables. Each solar table hosts a certain number of modules. So for example, if a solar table is made up of 2 rows of 8 modules in portrait, there are a total of 16 modules. If each module has a capacity of 400 watts, then each table will have a capacity of 6.4 kilowatts. If the array has 10 of those, then the total capacity is 64 kilowatts. And if the array's yield is expected around 1,000 watts, then it will generate 64,000 kilowatt hours per year. So each table has a certain capacity, which we are donating with a small p. That's given, so we should know what that number is. It also has a certain area, which is also shown, and it has a cost that is divided into both space cost and an equipment cost. As you can imagine, the higher the tilt angle, the taller the table is going to be, which means that it will cast a longer shadow on the table that's behind it. Therefore, the higher the tilt angle, the more space that the array is going to occupy. But it's not just that. We're also going to be talking about the minimum sun angle, which sometimes designers use to define or to denote the inter-row spacing between the modules. So, what is minimum sun angle? If you install a flat module that's facing straight up, so it has a tilt of 0 degrees, this module is geared to capture summer light. In other words, the sun is very high in the sky when it's producing most of its energy. If you break down its energy through a histogram, you'll find that the sun altitude is quite high for most of the time it's actually putting out power. On the other hand, if a module is tilted, it's actually more geared for lower sun altitude, meaning that it will require a lower minimum sun angle in order to capture light. And that's what's happening when you increase the tilt angle. So an increased tilt doesn't just cast a longer shadow, it requires that the inter-row spacing to be greater. So how much area does a single table occupy? That is given in equation 2, and in equation 2 we can see that it's basically a product of a module's normal height, its depth, and this term that we're going to call the depth factor, which is cosine theta plus sine theta over tan alpha, and alpha being the minimum sun angle. To determine the relationship between tilt and the minimum sun angle, I simply estimated 2 points and I did a linear regression. This is again not the point of the paper. On one hand, you want the minimum sun angle to capture that low sight intensity, but you don't want it to be too low such that your array has too much inter-row spacing that is redundant. It doesn't do you any good when it comes to producing at a low altitude sun. So this does require practice, but as far as this model is concerned, a linear fit will do just fine. As I mentioned, I used Nate's data to derive this relationship between yield and tilt, and I found that it's about, at a 0 tilt, it's about 1100 hours. So if it's flat, the module will generate 1100 hours per year, and for every degree towards south you tilt it up, it will produce about 5 hours per degree. Okay, again, the model, you don't have to sweat over an accurate model. 6% coefficient of variation is quite high. And given that we're going to be using a constant yield, we're not going to worry about degradation or any of that kind of stuff. We all want to look at just what is the relationship between tilt and cost per unit area. So we're going to run through 3 optimization exercises, okay? The first one is when we want to minimize the total area. The second one is when we want to minimize the total equipment cost. And then the third one is going to be a compromise between space and equipment cost. Let's start with the second one, which is the one that we are most familiar with. Typically, when we approach a client for small distributed generation systems, we want to minimize the total equipment, in other words, the total amount of modules that we want to install in order to produce a certain amount of energy E. In that case, we are essentially ignoring the space cost that's involved. And in which case, we will naturally gravitate towards that maximally producing tilt value, because it will allow us to produce the most amount of energy, thereby minimize the total amount of equipment that we have to spend. Well, for example, in page 8, this is a very common scenario that you could find yourself in. A fixed tilt solar array is to produce a certain amount of energy. Land will be purchased, but it's quite negligible. You don't have to worry about the cost of the land. Let's determine the system design, the system tilt, that will minimize the total system cost, which is essentially total equipment cost. Okay? So if we get rid of the space term in equation 6, we can see that now the cost function is Kp times E divided by Y. Kp and E are of course given constants, so there's nothing we can really do about them. So in order to minimize C, we have to maximize the denominator on the right hand side. So we have to pick a Y of theta that is the greatest, which means that we will pick that maximally producing tilt angle. And that is why we typically do that with small generation systems that have a negligible space cost. So now let's look at the opposite. Now let's say the exact opposite happens, and I've kind of did them in reverse just so we can start out with the easy one. So on page 7, a fixed tilt solar array is to be installed on an acreage by using the least amount of land possible. And that could be translated by saying land is very expensive here. Try to build this solar array to produce a certain amount of energy E per year at the least amount of space that's required. So what do you think the solution is going to be? Are we going to pick a maximally producing tilt angle that will reduce our equipment cost, or are we going to pick a very low tilt angle that will shrink the size of the array because there will be much less inter-row spacing? So given that the array has to generate in a certain amount of energy E, let's substitute equation 5 into 7 and we get equation 11. And in equation 11 we can see that the array's total area is again a constant multiplied by this z theta over y theta. Z theta is the depth factor, that cosine theta plus sine theta over tan, the minimum sun angle, and y of theta is that simple linear regression that we obtained from Nate's data. So now it's very clear what we have to do. In order to minimize a of theta, we have to minimize that z over y, both of which are functions of theta, which is tilt. So we can express our optimization here as follows. So let's plot z theta over y theta. As you can see, z theta on its own has a minima at 0, but even when you divide it by y of theta, the yield didn't play much part of it all. As you can see, when your tilt angle is 0, your depth factor is 1. But when you have increased your tilt angle to the maximally producing tilt angle, your space requirements almost tripled. So you can rest assured that if the client is very keen on minimizing space, you can't pick that 45-degree tilt angle because it will be much more expensive. The space requirements are going to triple, even though the maximally producing tilt angle produces about 45% more than the one at 0. So space costs do have a much larger incremental role than equipment costs. So now that we have looked at both extremes, we have looked at what happens when space doesn't cost much. We do what we do anyways, which is pick that maximally producing tilt angle. If space is very expensive, we found that it's actually better to use a 0 tilt angle. So in a nutshell, we can see that space costs can essentially overwhelm the incremental gains that you get with a higher tilt. So tilt angle when it comes to space plays a much more important role than it does when it comes to production. Up to this point, I've been talking about minimizing the total cost, but typically solar designers use levelized cost as their caliber when designing solar PV systems. So let's look at minimizing levelized cost instead of just minimizing cost. Again, if we go back to our expression for total cost, we can see that the total cost is directly proportional to the total energy requirement. And because levelized cost is total cost over total energy, dividing the right-hand side by E will yield the same result because, again, it's a constant. So minimizing our total cost is analogous to minimizing the system's levelized cost. Similarly, let's see what happens when we are concerned about maximizing the energy density. If we divide E by A of theta, we get the same ratio, or the reciprocal of the same ratio that we have seen minimize area requirements. Therefore, we can also say that maximizing your energy density is also analogous to minimizing your space requirements. So we kind of looked at both extremes, namely where space costs are negligible, and we concluded there that we will pick a tilt angle that maximizes energy production to minimize equipment costs, as we typically do today with small systems. And we also looked at when space costs are very high, and we saw there that a higher tilt angle plays a more dominant role, arrays space requirements than that incremental gain that you get with a higher tilt. But now let's consider a middle ground. Let's look at a numerical solution. So we'll throw some numbers in here. Given that we have an expression for the total cost, let's throw some numbers and look at that where that sweet spot is. Let's consider that we want to produce 100 megawatt hours per year. The table's normal height or length is 4 meters. Its width is 16 meters, and each table has a capacity of 12 kilowatts. And let's see what the optimal tilt angle is at different space costs. Okay, so we're just plugging in some numbers and we're plotting a graph here. You can see that when space costs are $0 per meter squared, the tilt that minimizes this total system cost is that maximally producing tilt. But as we increase, we can notice that there's a minima starting to appear. We can see that there is actually a tilt angle that's lower than 50, around 35 degrees. Okay, so we now have a model that can at least numerically and very quickly let us determine that optimal solution. But this is not where it's interesting. Let's go back and just treat this analytically again. So this is our total cost function. We can see that it's a function of theta. Let's take a derivative and set it to 0. Because when we do that, we actually get a very revealing result. We're actually going to tie the system's optimal tilt with the array's effective efficiency, PV efficiency. Okay, so this is the total cost function. Again, as I mentioned, we'll take a derivative, we set it to 0, arrive at equation 20. Let's just forget about the right-hand side. It doesn't really tell us much. What's interesting is what's on the left, specifically that P over LW. So what's P again? P is the table's capacity. LW is the table's normal area. So P over LW, that sounds a lot like, for example, if you have a 400 watt module and has dimensions of 2 meters by 1 meter, that's essentially the module's effective PV efficiency if you multiply it by 1,000. So what we have found is that the optimal tilt is directly related to the module's PV efficiency. Okay? And now and because we have an analytical solution, we don't have to go through the numbers at all. You can solve this once per region, and you can carry that in the back of the envelope as I've shown in this diagram here. As you can see, I've just plotted this equation for the data that I've used at NATE, and we can see that for different values of KPP over KA over LW, we're going to get different optimal tilt angles that deliver the total system, that deliver the minimized system cost. So you don't have to rely on Excel spreadsheets or any proprietary software to get this done. So what we have found is that the optimal tilt of the array is directly related to the efficiency of the array that we are using. And by that, we have to take into account the spacing between the modules and the spacing between the tables, because that will derate your effective PV efficiency. So just because you're using 18% efficient modules doesn't mean that your array is 18% efficient, because you have all this space that's used for clamps and used for inter-row spacing and for transformers and so on, that is essentially a derate on your efficiency. So you have to take into account that area in order to know what your effective PV efficiency is. It's essentially the area in your array that is not covered by modules. So what have we concluded? Well, we showed that if you really want to minimize space, because it's so expensive, you're going to pick a tilt angle of 0. Okay? We also showed that minimizing cost is essentially the same as minimizing levelized cost. And we also showed that minimizing area is also equivalent to maximizing energy density. And finally, we showed that the optimal tilt is directly correlated to the array's effective PV efficiency. This is explained a lot more thoroughly in the paper, which I highly recommend that you go through. Thank you so much for watching this video. Feel free to get in touch for any engineering work that you need with solar PV or microgrids at large.